AI can paint landscapes, write functional code, and draft essays in seconds. But to see how machines learn to create, we have to look back at a time when they were strictly literal. During the symbolic era of the 1950s, early artificial intelligence operated on human-coded if-then logic. If a user provided a specific input, the machine returned a pre-written response. This worked well for calculating math. But human language is full of ambiguity. It is impossible to write an explicit rule for every possible context, slang term, or nuance a machine might encounter in the real world. Because these systems could not scale or adapt, progress stalled. Funding evaporated and interest dried up during the periods historically known as the AI winters. Researchers realized that to build actual intelligence, they had to stop writing rigid instructions. They needed to feed the machines raw data and let the algorithms discover the patterns on their own. Intelligence could not be programmed line by line. It had to be grown. By the 2010s, neural networks reached a breakthrough in recognition. You could show a model 1,000 photos, and it would learn the exact visual traits of a cat with high accuracy. But visual recognition is a one-way street. A model that knows exactly what a cat looks like doesn't automatically know how to draw a new one from scratch. That bottleneck broke in 2014 with the invention of the Generative Adversarial Network, or GAN. This architecture used a competitive mechanic to force the machine to create. A generator creates fake data from random noise, while a discriminator tries to identify those fakes. Every time the discriminator catches it, the generator is forced to refine its output. This loop continues until the generated images become indistinguishable from reality, fooling the discriminator. This chart shows how research shifted toward a newer technique called diffusion models. GANs were often unstable to train, leading researchers toward a process that masters the structure of noise itself. In a diffusion model, the system is trained by systematically destroying an image. It adds randomized visual noise until the picture is reduced to pure static. The model then learns to reverse that process, clearing the noise to generate entirely new, original images from scratch. Mastering this mathematical structure of noise proved that machines could synthesize new realities simply by understanding the patterns hidden within chaos. However, text presented a very different problem. Early language models processed words one by one. By the time they reached the end of a long sentence, they often lost the context of how it started. The turning point came in 2017 with a paper titled "Attention is All You Need," which introduced the transformer architecture. Transformers use self-attention to process all words in a sequence at once. The model weights the importance of every word relative to every other word, regardless of position. This parallel processing allowed models to map human language at a previously impossible scale. This led to the scaling law. By feeding a transformer massive internet datasets and increasing its parameters into the billions, developers created large language models. At this scale, the models exhibited emergent abilities. They began to reason through logic puzzles and write computer code, despite never being specifically programmed for those tasks. To the machine, human language transformed into a multi-dimensional mathematical landscape that it could navigate with surgical precision. Generative models construct original concepts by blending patterns extracted from millions of sources, rather than following a linear path from input to output. However, because these systems operate on statistical probability rather than verified facts, they can confidently invent false information, a phenomenon known as a hallucination. Solving this requires a process called reinforcement learning from human feedback, or RLHF. It is an engineering shift towards safety and ethical alignment. RLHF uses human testers to manually grade model outputs. By rewarding accuracy and penalizing toxic or false responses, developers align these probability engines with human truthfulness. These systems now function as powerful synthetic collaborators, built directly from the deep patterns and immense